Welcome back to multiple choice section, question 32. What is the solution to tan phi equals secant phi? This is a trigonometric equation, and we'll start solving it by first replacing both tan and secant by terms that contain sine and cosine. So tan phi will be sine phi over cos phi, and secant is 1 over cos phi. We'll take the 1 over cos phi to the left side, so all terms to one side of the equation. And we'll leave just 0 on the other. So next we want to factor. To solve by factoring means that we need to check and see if we have any common factors first. And as you can see, cos phi appears in the denominators of both terms, so we'll take that out. So 1 over cos phi is the common factor, and then in brackets we'll have sine phi minus 1 equals 0. So as you can see, we have a product of two different factors, and to solve we'll make each of them equal to 0. Let's see how this turns out. So 1 over cos phi equals 0, or sine phi minus 1 equals 0. So if you look at the first part of the equation, so 1 over cos phi equals 0, you see that here we have a constant in the numerator, and when a constant is in the numerator, it doesn't matter what the value of the denominator is, the value of the entire rational expression won't be equal to 0. So it will always be different. So therefore, we're going to say that we get no solutions from this factor. So sine phi equals minus 1 equals 0 means that sine phi must be 1. So angle phi is inverse sine 1. And if you use the calculator will give you either angle 90 or pi over 2 radians. So this would be our first solution. So I'm going to take the solution and check and see how this fits into the equation. Check and see if this works first. So if we want tan phi to equal secant phi, or phi equals pi over 2, we'll have tan pi over 2 equals secant pi over 2. Try to use the calculator and see if this is true. So most likely your calculator will tell you that there is an error. And the reason why we see an error there is because at pi over 2, if you look at the graph of the tan function, we'll see that the tan function will have a vertical asymptote, which means it's undefined. And when a term is undefined at a specific value of x, it means that that value of x cannot be a solution to the equation because the term is non-existent there. If you look at it from the unit circle point of view, so for example, here is the unit circle, the value of tan will be y over x. And for the angle 90, which is right here, the value of x will be 0 and the value of y will be 1. So the tan ratio is 1 over 0, which is undefined. So therefore, we're going to say that there are no solutions to this equation. So option A is the correct answer. Next, we have question number 33, and this is the last question in the multiple choice section. A graph must never cross which of the following? A vertical asymptote, a horizontal, oblique, both A and B, or all of them. If you remember, when we graphed rational functions, initially we looked at the reciprocals, and we said that the function of rational functions can have vertical and horizontal asymptotes, and that was the typical shape of rational functions we visited first. And then we looked at more complicated rational functions, such as functions with more than one vertical asymptote. And in some of them, we saw that if the function had two vertical and one horizontal asymptote, so a typical shape that we looked at was this. So still, the function didn't cross vertical or horizontal asymptotes, but in some of them, however, we noticed that the graph was crossing the horizontal asymptote, but never the vertical. So, for example, in this function in here, we saw that the graph would be one piece of the graph here one piece of the graph will go here and the other one will go here, right? So the horizontal asymptotes, we've seen them crossed by the graph, but the vertical asymptotes are never crossed by the graph because the vertical asymptotes state or define restrictions in the domain. And if a value of the independent variable is restricted, then the function cannot actually cross that restricted value. So in this case, I would say that the graph must never cross the vertical asymptote. Even when we're able to remove the asymptotes, remember the removable asymptotes, for example, when we had the functions y equals 3x minus 3 over x minus 1. So the restriction was at 1. But because this function simplifies the restriction, and the function becomes y equals 3, when we graph this function, we draw the line, so we draw the graph, but still at 1, we will create a hole because that's where the vertical asymptote used to be. So this is the end of the multiple choice section. I hope you find this useful. Thank you for learning with me and